Hello, everybody. This is the lecture for section 4.6, limits at infinity and asymptotes. So we're going to take a step back really quick. We're going to go back to limits. This section does have derivatives, but we're going to be using them for something else a little later. We're going to start being able to graph functions without using a graphing calculator, using all the calculus that we've learned up to now, okay? But first, before we get to that, like I said, we're going to take a step back to limits at infinity and asymptotes. Basically, we're going to be um, revisiting some stuff from pre-calculus that you guys might remember. Okay, back in pre-calculus, there was a bunch of shortcuts that you probably learned how to do so that you can find limits of this thing and limits of that thing, right? They were just shortcuts back then. There was no real, we didn't understand why, we just took them at face value. And then just sort of went on with pre-calc, right? Now that you're in calculus, you actually get to see the reasons why it works out the way it did, okay? So that's what we're going to do here. All of this is going to be, like I said, to learn how to actually graph them, okay? So the first thing I want to do is I want to recall some stuff from pre-calculus, from your pre-calculus course, okay? So really quick, if you guys remember, right, if you want to find x-intercepts, that's the y equals 0, and then you solve for x, right? For the y-intercepts, it goes backwards. You set x equals 0, solve for y, okay? To find vertical asymptotes, right, most of the time, you would go and find where the function is undefined, okay? Very rarely do you not end up doing this in order to find a vertical asymptote, okay? The two big ones of note, if you had a rational function, so some polynomial divided by another polynomial, right? You found where the divide by 0 rule appeared in the problem. So you would find everything that would make you divide by 0, throw those out, right? Those values that you threw out were going to be your vertical asymptotes, right? And then for logarithmic functions, right, you found that x values where the inside of the logarithm became negative, okay? Wherever that happened, that's where you're going to have a vertical asymptote, right? And if you wanted to find horizontal, oblique, or slant asymptotes for rational functions in particular, something that looks like this, right? A p of x over a q of x, a rational or a polynomial divided by another polynomial, right? There were just these three rules for now. If the degree of the top was bigger than the degree of the bottom by 1, right? You had to use long division or synthetic division. Whatever came out from that, that was going to be your oblique asymptote, right? If the degree is equal to the degree of the bottom, if the top and the bottom have the equal degree, then you got to divide the leading coefficients. That one was simple enough, right? And then the last one was if the degree of the top was less than the degree of the bottom, you automatically had asymptote at y equals 0. These were the things that you sort of just had to memorize, right? Okay. So in this chapter, we're going to actually find out how these three actually worked. Okay. Like I said, we took these at face value before, just saying, okay, that's got to be it. So memorized it, put it on a flashcard, and that's it, right? In calculus, now we're going to actually prove these. Okay. So really quick, what I want to do first, okay, is I want to go ahead and do this example really quick. So here's a polynomial or a rational function, right? And what we're doing is going to find the x, y intercepts and the horizontal and vertical asymptotes. Okay, so let's do the x and y intercepts first. So x intercepts first, right? If you remember for x intercepts, we want the y equal to 0, right? And then solve for x. So that means my f of x minus 3x squared minus 6x minus 3 all over x squared plus 4x plus 3. That's got to all equal 0. If I have this equal 0, then that means, right, that minus 3x squared minus 6x minus 3, that has to be equal to 0. Since I have a fraction that's equal to 0, the only way that's going to be equal to 0 is if the top is equal to 0. I am going to factor out a nice negative 3. I get left with x squared minus 2x, or plus 2x, plus 1. And I know that this factors to x plus 1. x plus 1. So therefore, both of these tell me that x is equal to -1, -1, x equal -1. So then my x-intercept is going to be at -1, 0. Right? Okay. Y-intercept now. This one's the easier one. The y-intercept, right, is when the x is equal to 0, right? So all I get to do is just f of 0, right? -3, 0 squared minus 6 times 0 minus 3 all over 0 squared plus 4 times 0 plus 3 -3 over 3 -1. So my y-intercept is going to be at, what's at? 0, comma, -1. Okay. Hopefully we're good for now. Okay. Let's do vertical asymptotes first. So vertical asymptotes. So we have a division here, right? You notice we have the division here. We're going to find, basically what we're doing in essence is find the domain at the same time as finding the vertical asymptotes, right? So f of x is going to be equal to the -3, and I'm just rewriting, -6x minus 3 all over x squared plus 4x plus 3. Okay. We know that the top factored out to this thing over here. So I'm just going to go ahead and do that already. -3 x plus 1, x plus 1, right? And then the bottom factors too. That factors to x plus 3, x plus 1. Okay. Now, you guys can see here that there is a x plus 1 on the top, and it can cancel out with x plus 1s on the bottom, right? If you guys recall, this cancellation that happened here produced something specific in a graph. And that thing was a removable discontinuity, right? Or what it's called more sort of commonly, it was a hole. Okay, a removable discontinuity is the same thing as a hole. There were just two different words for it, right? What got left behind was this, -3 x plus 1 over x plus 3. Okay. Whatever got left behind on the bottom, so this thing in particular right here, whatever got left on the bottom, that's what was going to give you your vertical asymptote. So this tells me, so technically what I'm trying to do here is find when x minus 3 plus 3 is equal to 0. That means x has got to be equal to -3. So our vertical asymptote is at x equal -3. Okay. Now let's go ahead and find the horizontal asymptote. So the horizontal asymptote, we're going to go ahead and do, I'm going to rewrite it again, f of x x squared plus 4x plus 3. If you guys remember from the things that were mentioned up top here, there were these three options right here, right? A, B, and C. If the degree of the top is greater than 1, we had an oblique. If the degree of the top was equal to the degree of the bottom, divide the leading coefficients. And if the degree of the top is less than the degree of the bottom, then automatically you just had a horizontal asymptote at y equals 0, right? So what we really just cared about was the degree of the top and of the bottom, if you guys remember. So we only cared about these two things, right? So then that meant it was going to be a negative 3x squared over x squared. X squared here and the x squared here canceled. So then therefore, according to our thing from pre-calc, y equal -3 was going to be our asymptote, our horizontal asymptote. So therefore, horizontal asymptote at y equal -3. So now I'm going to open Desmos. I'm going to bring Desmos in here. Okay. And I'm going to go ahead and type in. I'm going to go ahead and type in my my function, right? Let me go ahead and move this over. Scooch this over a little bit right there. Okay. -3x squared minus 6x minus 3, all divided by x squared plus 4x plus 3. So look at what we have here. This is the actual graph, right? So there's a couple things I want to note here. First of all, let's take a look at our x and y intercepts. Our x-intercept is going to be at -1. That looks like -1. And then our y-intercept is going to be at 0, -1. There's the other one. Cool. Uh-oh. What I wanted to do. Okay, I don't know what happened there, but okay. And now our vertical asymptotes was at -3. And lo and behold, let me see if I can scooch that in a little bit. That looks like -3 right there. Look at how it's hugging the -3 line there. And then the very last thing, my horizontal asymptote was going to be at y equal -3, right? So if we sort of pull this out really far, you guys can see that it's doing the exact same thing, but at -3 for the y, okay? Okay, so all of our work for now has checked out, right? So we're finally going to get into how this how all of these ideas were developed from calculus, okay? And we're still going to be using an informal definition here because we're not going into the nitty-gritty definition of a limit. There is an actual much more mathematical definition of a limit. We're not going to cover that in this class. We're just getting a feel for it, really a heavy feel for it, okay? So the informal definition, right? First of all, we're going to be taking the definition of a limit that heads toward infinity, okay? So suppose that your x values become sufficiently large, positive or negative. So we're basically saying that our x values are getting very, very, very big, either negative or very, very big positive, okay? And whenever that happens, we write this right here. Either that or that. So this is telling us that the limit as x approaches infinity of f of x is approaching a value L, okay? Or the other one, the limit as x approaches negative infinity of f of x is approaching a value L. Does that make sense? Okay, and now we get to go into a definition that's much more explicit about a horizontal asymptote. It's whenever these two things head to a specific value L. That line, the y equal L, is our horizontal asymptote. Okay. So in the quick checks, I just want you guys to try out the stuff that we just did. Okay, just find the x-intercepts, find the y-intercepts, find the horizontal asymptote, and find the vertical asymptote. Okay, use the stuff that you remember from pre-calc. Okay, only odds and evens. So I'll be checking these and providing answers in the notes in a little bit. Okay. All right. Another informal definition, so that we can get more used to the notation of a limit. We say that a function f has an infinite limit at infinity. We write it this way, right? If f becomes arbitrarily large for sufficiently large x values, positive or negative. And likewise, we can write negative infinity, right? That means that it has a negative infinite limit, or a limit of negative infinity, if it becomes arbitrarily large, sufficiently large for any x values, positive or negative. So basically what this is saying is, if you're going either positive infinity or negative infinity, right? And your y values just keep growing and growing and growing upward, right? Then that means you have a infinite limit at positive infinity. That'd be the first one, right? And then likewise, if you go toward x equal positive infinity or negative infinity, so in any one of those directions, and your y values just keep nosediving, they keep going down, right? Then that means you have a limit of negative infinity. That's it. Okay. So what did we use this for? If you guys remember, again, from pre-calc, let's say you want to determine the end behavior for a funky looking polynomial like this one that I have here, right? We used it to determine end behavior, what our graph was doing at the end. Okay, so if you guys recall from pre-calc, right? Let's say you had x to the n, right? If n was odd, then what you had as a graph was going to be a squiggle. It was going to do this. It was going to do some sort of S, right? And if n was even, you had a U-shaped, right? You had a U-shape. It did this, and then it did a couple squiggles, however many squiggles it did, and did that, right? And let me actually rewrite n. N actually did sort of, it came up from below, did as many squiggles as it wanted here, and then sort of shot back up that way, right? So that's how you guys remember doing end behaviors from calculus, right? And in order to find out which one you had, you only had to look at the front term, okay? The very beginning term. So since this is a x to the eighth, that meant we were messing with something that was even. Since there's a -2 up front, you could, the graph meant it was flipped. So the graph of this, let me do it down here, the graph of this thing is probably going to do something like this. It's going to start from down here, squiggle a bunch of times, and then head back down. This gave us the picture of what we needed, right? So in order to determine the end behavior now, we're going to be using this thing right here, right? We can do now the limit as x approaches infinity of f of x, that is going to be equal to negative infinity. Since this end, let me actually draw it in green, this end down this way. So this is toward positive infinity, right? This end kept going downward, so and therefore the limit is going to be negative infinity. And then likewise, the limit as x approaches negative infinity of f of x was also going to be negative infinity. That was the other end. That was this end over here. That as we kept on going that way toward negative infinity, my y values kept on shooting down. Okay. Again, quick check. These should be pretty quick. You can verify these with a graphing utility if you need to, okay? So now, from pre-calculus, we know how to find these things sort of pretty quickly, right? But we were never given the justification for why, correct? We just sort of took them, like I said at the beginning, at face value, and then we just moved on with our lives, correct? So now we're actually going to be using some of our some of our calculus knowledge to actually compute why these things are, okay? And it gives us a process to compute some that are a little bit more difficult, okay? And it all comes down to sort of like these ideas right here, okay? These aren't in the book, but they sort of encapsulate sort of the sort of like your thought process that you're going to need to have while computing some of these limits, okay? So let's go ahead, take the limit as x approaches positive infinity or negative infinity, right, of something really big, right, divided by something really small, okay? When you have something that looks like this, right, then you know that something big divided by something small, this is still going to produce something big, right? So when this happens, you know that this thing is going to be probably going towards something like infinity, right? Okay. For the next one, it's the same idea. So suppose you have something small being divided by something big, and the x value is getting infinitely bigger, either positive or negative, right? So if you're getting something small being divided by something big, okay, then this right here is going to end up becoming very, very small, right? Small, right? And when this happens, this tends to go to 0, okay? These two that I just did aren't in the book, but they encapsulate sort of like the idea, like I said, the idea that you should be having when you're doing these kind of problems, right? The last one here is in your book. So let's say, now we're actually sticking in mathematical terms here. Let's say that you have the limit as x approaches positive or negative infinity, right, of c divided by x to the n, right? As x gets infinitely bigger, either positive or negative, right? So remember, so just let's note this first, that c is a constant value. C is a fixed number. So 5, 22, negative 800, something, right? It's a fixed number, right? So this gets infinitely big, right? That gets infinitely big. Sorry, look at me go. C is a constant value. The x to the n is getting infinitely bigger and bigger and bigger and bigger, right? So what we have here, right, is something that is sort of small, right, being divided by something that's getting bigger and bigger and bigger, right? So then this is going to be equal to 0, okay? So why did I have to show you guys this? I'm going to go ahead and determine the end behavior for this graph right here. So notice for this one, right, we can't use the rules that we learned in pre-calc. So what do we do? So what we're going to do now is, this is basically going to give us the justification for why the rules that we learned in pre-calc are the rules that we learned. Okay, so I'm going to go ahead and rewrite. So what I'm going to do here is I need to find the limit as x approaches positive or negative infinity of 3x minus 2 over the square root of 2x squared plus 1. Okay, what I'm going to do is I'm going to multiply by the biggest, the 1 over the biggest power that I see. Okay, so let me actually write it out over here. So the biggest power that I see And this is going to be crucial that you guys do this, is an x squared that is inside a parentheses, or inside the square root, right? So I'm going to multiply by 1 over the square root of x squared. Okay, if you guys look at the videos online in your homeworks, they say divide by the highest power. This is equivalent, multiplying by its reciprocal. Okay, so I'm going to rewrite some stuff now. This is going to be equal to the limit as x approaches positive or negative infinity, right? This is going to be now 3x minus 2 over the square root of x squared, all over the square root, and I'm going to collapse some stuff here. I'm going to do a big, huge square root of 2x squared plus 1 over x squared. So this is going to be an exponent rule way back from calculus, okay? So just make sure you're able to do it. I'm going to reduce some stuff now, okay? The square root of x squared, that's going to be just x, right? So then this is going to reduce to, the top is going to reduce to the limit. Let me write the limit as x approaches plus or minus infinity. So this is going to be 3 minus 2 over x divided by the square root of 2 plus 1 over x squared. Okay. Nothing horrible yet. So now we're going to be able to use this idea that we just presented up above, right? And the way I'm going to do it is, good thing I have that many highlighters, I'm going to look at the limit of each one of these. As I take the limit as x approaches infinity. Okay. So I'm going to color code these a little bit. So this limit, the yellow limit, right, is going to be 3. That is, as I take this limit right here, so the limit as x approaches of 3, that is just 3, okay? The next one, the one in the blue, right? The one in the blue, let me make this a little, there we go. So I'm going to be taking the limit as x approaches infinity of this thing, of 2 divided by x. So notice here's where we're going to use that idea that we did before, that I presented before, that my x values are getting infinitely bigger, right? So those are on the bottom. 2 is a fixed number. So then this thing is heading towards 0. So that limit of the blue thing is going to be tending towards 0, right? Next one. The 2, so I'm doing this limit now. Basically, the limit as the square root of 2, right? That's just going to be the square root of 2. The x variable means nothing here, right? And then lastly, the thing in the pink, right? So I'm taking the limit as x approaches positive or negative infinity of the square root of 1 over x squared, right? Again, we're going to be using that idea, right? My x's are getting infinitely bigger, whether they be positive or negative. 1 is a fixed number, so then this thing tends towards 0. Right? So what you would probably be seeing in the, let me write out what you'd probably be seeing in a video online or in the homework, is this, that you're going to see that now this is going to be equal to 3, right? Minus the limit as x approaches positive or negative infinity of 2 over x divided by the square root of 2 plus the limit as x approaches positive or negative infinity of 1 over x squared. Okay, this is what you, like I said, this is what you'll see in online videos and stuff. They'll say that this tends towards 0. This does the same, tends towards 0. So therefore, your answer is going to be 3 over the square root of 2. 2. And we are done. Okay. Since we were determining the end behavior here, right, this automatically gives us that we have a horizontal asymptote. Whoa, what was that? Okay, we have a horizontal asymptote at y is equal to 3 over the square root of 2. Okay, so now let's go ahead and go back to Desmos. And let's plug this bad boy in, see what we get. So 3x minus 2 divided by square root of 2x squared plus 1. Okay, so notice what's happening, okay, that as we go to positive infinity, did I take it in wrong? No, I didn't. I'm going to go ahead and do y equal 3 divided by square root of 2. There we go. There's one of our asymptotes. You guys see, as we go farther and farther out, it's hugging the line. You see how good that is, huh? There it is. Boom. Cool. Okay. The next thing that comes up is the quick check. So go ahead and try these out. Okay. We are now ready to start graphing stuff without using the graphing calculator. And this is going to be more, I mean, we can actually graph this stuff, right? But what we're doing more is we're using all the calculus that we've learned up to here to be able to find out how a graph behaves, basically, okay? All the stuff that we've learned up to just this section right here gives us a pretty good game plan of how to do it. And that's this right here. All of these 6 steps right here. So this is the problem-solving strategy for drawing a graph of a function. I copied these out directly from the textbook if you don't want to look at the textbook. Okay, so let me go through them really quick. Number 1, find the domain of your function. That should be easy. Find where, basically take out all the points where you divide by 0 or take the logarithm of a negative. That'll give you your domain. Number 2, locate all x and y intercepts. Okay. Number 3, determine the end behavior of a function. So that means you have to find the limit as x approaches positive infinity and x approaches negative infinity. Okay. Number 4, determine whether f of x has any vertical asymptotes. So this you can double check with part 1. Usually when you find the domain, it's going to give you where the vertical asymptotes is going to be, right? Number 5, find the critical value. Find all critical points, and from using the critical points, use the test for increasing or decreasing from our previous section to determine when they are increasing, when they are decreasing. Okay, and find any extrema that you might have. Okay, and then the very last step, number 6, is calculate the double prime and find when you have concavity changes and any inflection points. Okay. You can also use this to find any other local extreme, okay? All right, so this example has an entire page blank for it, and a graph at the end. So this is going to be pretty long, okay? But we're going to follow this this right here, this the problem solving strategies to actually try to graph this out. Let me zoom in a little bit and make this sort of flush in the middle. Boom. Okay, there we go. Okay, so here we go. We want to sketch a graph of this thing using our problem solving strategy. So number one, I'm going to go down the list from 1 through 6. Okay. So number one, right? We need to find our domain. Okay. So our domain is going to be, so here's my f of x squared over x squared minus 9. So I'm going to go ahead and try to factor this out. So whenever you try to find the domain with something like this, try to factor it out. So x squared over x plus 3, x minus 3, okay? So if we take a look at this, we automatically see that our domain is going to be negative infinity to negative 3, union negative 3 to 3, union 3 to infinity. I cannot plug in negative 3 and positive 3 because if I do, I divide by 0. Nothing canceled, so there are no holes. So we're good to go. Yeah. Number 2, find x and y intercepts. So let's do x intercepts first. So for x-intercepts, we let y equal 0. So that means x squared over x squared minus 9 has to equal 0. Therefore, x squared has to equal 0. Therefore, x has to equal 0. So x-intercept at 0, 0. Right? Y-intercept. That means the x has to be 0. So I have to do f of 0. 0 squared over 0 squared minus 9. This is 0 over negative 9. That is 0. So the y-intercept just so happens to be our x-intercept. 0, 0. We're good to go. We are good to go. Okay. Step 3. We need to find the end behavior. So we need to find the limit as x approaches infinity of f of x. I'm just going to go ahead and write it in. So x squared over x squared minus 9, right? And I'm going to go ahead and do the positive and negative infinity, since both of these are going to be taken care of by just one fell swoop, okay? That's going to be the limit. So I'm going to divide by the highest power, right? Or multiply by its reciprocal as x approaches positive or negative infinity. So it's going to be x squared over x squared on top divided by x squared plus 9 over x squared on the bottom. So this leads me to limit as x approaches positive or negative infinity of 1 over 1 plus 9 over x squared. I'm going to do what you would see in the videos. This thing is going to tend toward 0, right? 9 divided by x squared. As my x gets bigger and bigger, that's going to be 0, right? So then this is going to be equal to 1. So my horizontal asymptote is at y equal 1. Okay. That was step 3. Step 4. Determine if x has any vertical asymptotes. Like I said, we can double check this using step 1. So step 4 tells us that we can factor it out this way, right? So then therefore, either x, whoa, wrong thing, wrong pen. Come on, there we go. X plus 3 has to equal 0, in which case this gives us x is equal to -3, or x minus 3 has to equal 0, in which case x is equal to 3. So then there's vertical asymptotes at x equal positive and -3. Okay, here comes the fun stuff. So let's go ahead and do no 5. 5 is where we need to find our critical points. Five is where we need to find our critical points. So we need to find, so I'm going to rewrite it. F of x is equal to x squared over x squared minus 9. This means we have a high and a low. So then therefore, arrange myself here. There we go. F prime of x is going to be the low. So x squared minus 9 times d high, so 2x, minus high, that's going to be dx squared, times d low, 2x, all over the bottom squared, x squared minus 9 squared. Let's go ahead and try to simplify this a little bit so that we're going to have 2x cubed minus 18x minus 2x cubed all over the bottom, x squared minus 9 quantity squared. Okay. This is a positive, this one's a negative. So we have this. This is what it reduces down to, our derivative. Minus 18x over x squared minus 9 quantity squared. In order to find inflection points, this has got to be equal to 0. So therefore, negative 18x has to equal 0, which means x has to equal 0. So that means we have a minimum at x equals 0, right? Notice that before, our x-intercept and our y-intercept were also there. Okay. Okay, so now what we have here is everything we need. We're going to do the first derivative test. Okay. So let me do first derivative test. So we can determine where it's increasing or decreasing, right? So I'm going to draw my number line. Okay. X equals 0 is one of our critical values, okay? And positive 3 and negative 3 are our other critical values. I'm going to make this a little longer so I can actually write some stuff below. 0, 3, negative 3, right? Those are our critical values. So remember, for a critical value, it's when the derivative is equal to 0 or when the derivative is undefined. That derivative is undefined at positive and negative 3. It just so happens that those were our asymptotes as well, okay? So let's start doing this, okay? So I'm going to go ahead and pick some representative values. So this is going to be, let's try -4 over here. Let's try 1. Let's try 1. And let's try 4. And I want to plug it into my derivative. So I'm going to go ahead and rewrite my derivative over here. F prime of x is going to be equal to minus 18x over x squared minus 9 squared. All right. So when I plug in the -4, so it's going to be -18 minus 4 all over minus 4 quantity squared minus 9, and all of that squared. So this is going to be something. 16 minus 9. That's something. My arithmetic ain't too good. Let's try the top. 18 times 4. That's going to be, I think that's 52. Hell, I have a calculator. Why don't I do that, huh? 72. Positive 72 over 16 minus 9. I believe that's going to be 7 squared. Remember, I don't care about the value itself. I care about the sign. That's going to be positive. Okay, let's move on to 1. Okay. So minus 18 times 1, but negative 1. Forgot to put the negative. That's supposed to be negative 1. Not bad. All over negative 1 squared minus 9 quantity squared. So this is going to be positive 18 all over 1 minus 9. That's going to be negative 8 squared. And this is positive. Okay, so let me finish up with the first derivative test so that we can conclude something from here altogether rather than in pieces. I'm going to do negative 18. I'm going to plug in 1 this time. 1 squared minus 9. This is going to be now negative 18 over negative 8 quantity squared. This right here now is going to be a negative number. Okay. Last one. Negative 18 times 4 over 4 squared minus 9 squared. This is going to be a negative 72 over 16 minus 9. That's going to be 7 squared. This is going to be negative. Okay. So if you recall from first derivative test, if the sign is the same before and after your critical value, no conclusion could be made. So at negative 3 and positive 3, we can't make a conclusion. However, though, from a previous portion of this problem, we know that this is going to be asymptotes. So no big deal there. But here, it went from positive slopes to negative slopes, right? So then that means right here, this means that there's a positives on one side, right? And then negatives on the other. We've got a maximum. So this is telling us that there's a max at x equals 0. That's number 5. Finally, now number 6. I'll go ahead and do it down here. 6. I need to find points of inflection and concavity. Determine the concavity, right? So what I'm going to do is I'm going to find the inflection points first. So then my f prime of x, I'm going to rewrite that. That's going to be negative 18x over, where is it? There it is. X squared minus 9 quantity squared. I need to find the second derivative now, right? So f double prime of x is going to be my low, so x squared minus 9 squared times d high, so negative 18, minus high, minus the high, minus 18x times d low. Here's where the fun begins. So it's going to be 2x squared minus 9 times 2x all over the bottom square. So it's going to be x squared minus 9. Before I forget, to the fourth. Okay. Let's simplify the top a little bit, yeah? I'm going to keep the x squared minus 9. So what I'm going to do is this. Watch this. This is what I mean by trying to be elegant with your arithmetic. There's an x squared plus 9 in everything up top. So that's exactly what I'm going to do. I'm going to pull out an x squared plus 9. X squared minus 9, sorry. So what gets left is a minus 18 plus 18x times 2. Oh, whoops. Look at me go. This one was squared, so I get left with one of those two. X squared minus 9. Let me write it down below. Yeah? This is going to get nasty. X squared minus 9. So there's going to be an x squared minus 9 times negative 18 plus 18x times, this is gone, 4x all over x squared minus 9 to the 4th. Okay? I'm going to reduce a couple things here. 1 to the 4th gets to cancel one of those out. So therefore, let me bring my calculator out. I'm going to have now on the top negative 18x squared plus 162 plus 18 times 4. That's going to be 72x squared all over x squared minus 9 cubed now, since we got rid of one of those x squared minus 9. Okay? To reduce it one more time, so minus 18 plus 72, 54. So 54x squared plus 162 all over x squared minus 9 cubed. This is my f double prime of x. Okay, so let's go ahead and now find the inflection points. So then we need this equal to 0. So then therefore, the top 54x squared plus 162 has to equal 0, right? So then x has to be plus or minus. Whoa. Something tells me I forgot something. Oh, we didn't. Negative 162 over 54. So we have this as, and these are plus or minus. Notice that we're taking the square root of a negative, right? We are taking the square root of a negative. So then therefore, this one doesn't have inflection points when setting it equal to 0. So because this is negative, right here, this is negative, no inflection points this way, okay? There are two other inflection points though. So remember, inflection points are when the second derivative is equal to 0, right? Or when the second derivative is undefined. So there's always that little bit of undefined that people forget, right? Okay, so f double prime of x, right, is undefined at x equal positive and negative 3 because of the denominator. Okay, so we've got everything we need now. We're going to do test for concavity. Test for concavity, right? So then this one required you to use, again, the number line. Okay, negative 3 down here, positive 3 up here. Notice that this one doesn't have 0 because 0 was a critical value, right? Not an inflection point. Okay, so again, what we're going to do is we're going to choose representative points. -4. We're going to choose 0 as the representative point here, and then 4 over here. F prime, F double prime, sorry, is that thing that we found right here. Let me move this over a little bit. F double prime of x, 54x squared plus 162 all over x squared minus 9 cubed. Okay, we are off to the races. So, 54 times -4 squared plus 162 all over -4 squared minus 9 cubed. -4 squared, that's going to turn it positive, times a positive, that's still positive, plus a positive, that's still positive. Okay. -4 squared, that's positive. That's going to be a positive 16. Minus 9, that's still going to be positive. And then you cube it, that's going to be positive. You guys see where this is going? So this is going to be positive. Write that a little smaller. So the number here is going to be positive. And from a test for concavity, that tells us it's going to be concave. Okay, let's do 0 now. So 54 0 squared plus 162 all over 0 squared minus 9 cubed. 0 squared is 0 times 0. We get, let me actually do it over here on the other side. It's going to be equal to 162 over -9 cubed. So it's going to be a -9 cubed, right? This number is going to be negative. So then therefore, this is telling us that our graph is going to be concave down. Let's do the very last point. 4. So it's going to be 54 4 squared plus 162, all divided by 4 squared minus 9 cubed. We've got all this math already done over here. That's going to be positive. So then therefore, this graph is going to be, come on, there we go. It's going to be bold up somehow this way. Whew, that was a lot of work, wasn't it? Okay, so now what we're going to do is we're going to summarize all of this work into a graph. We're going to try to sketch it down here. Okay, so I'm going to do 1 and 4 at the same time, right? So number 1 and number 4 tells me that my domain is going to be that right there, this right here, right? And that also gives me my vertical asymptotes at positive and -3. So I'm going to go ahead and go to positive and -3. Okay. +3, -3. I'm going to do them in red. 1, 2, 3 right here. I'm going to zoom out a little bit so I can get most of, oh, there we go. Okay, that's good. -3 is right here. +3 is right here. Okay. So 1 and 4 are done. I'm going to go ahead and highlight them in green to denote that I did them already, right? Okay. We have an x-intercept and a y-intercept at 0. So I'm going to go ahead and scroll back down. And it's going to be 0, 0. So I'm just going to draw a dot right there. Okay. So number 2 is done. Number 3. Our end behavior, our horizontal asymptote, is at y = 1. So I'm going to go ahead and scroll back down. I'm going to do this. I didn't label, right? -3, +3. I'm going to make this right here equal to 1. So whenever you do your work, whenever you do your graphs, you're entitled to make whatever decisions on the graph that you want. Just make sure they're consistent. That's it. Okay. So I have my vertical and horizontal asymptotes done. Okay. So now 5 and 6, we have to sort of semi-do sort of together, right? So yeah, at 5, everything before -3 has to be increasing, right? And that's from the first derivative test. And from the second derivative test, or sorry, for the test for concavity, it is supposed to be bold up, but it has to fit in those asymptotes that are right there. So that means only one thing. It's got to do something like this. If I draw it in the other end, right, the slopes will be decreasing, right? Okay. Go back up here. At 0, we're supposed to have a maximum, right? At 0, we're supposed to have a maximum. Before 0, the slopes are supposed to be increasing. After 0, they're supposed to be decreasing. And between -3 and 3, it's supposed to be concave down. So that means only one thing. It's sort of rounding out the work for us, really. It's got to do this somehow. It's got to go up, hit that thing, and then come back down. We know that that 0 point, this point right here, has to be a maximum. So thankfully, all the work that we've been doing sort of pushes us in that direction, right? And then the last one, right? After 3. After 3, the slope's got to be decreasing, right? But bold upward. So the slopes have to be decreasing from first derivative test, but bold upward, so concave up, because of the test for concavity. Okay, so that means, sort of rounds out the work here, right? That is still concave up, yet the derivatives are decreasing. The slopes of the tangent lines are decreasing. You guys see that? If we were to draw it over here, right, we'd violate both of the first derivative test and the test for concavity. If we draw this one, second swoosh right here, right, this is bold downward, so this is concave down. We can't have that, right? And the slopes are increasing. Can't have that. So it's got to be that. Okay, and that's it. Notice how much we are able to graph just from using calculus, using all of our steps, all of our previous sections. Okay, and I believe that's it for this section. Let your questions come up. If you guys have any questions on this is going to be real tough for everybody. If you got any questions on it, don't hesitate to stop by my office hours, my Zoom hours online, shoot me an email, or shoot me something through a discussion. We can figure this one out. So this one, take a little bit of time on it, okay? As always, since we're doing a lot of graphing here, you can go ahead and use a graphing utility, whether it be a graphing calculator or decimals, just to verify if you're doing everything right, okay? That is perfectly fine, okay? Besides that, hopefully you guys are studying real hard, and I'll see you guys around.